Thanks, Oliver. Hi, guys. Thanks for attending our session from simple log to sophisticated crypto. My name is Arnold, as already introduced. I'm here with my friend and colleague, Hido. We both live in Israel and work as malware and threat researchers at the company named Morphisec. And today, we want to share with you our story on discovering the Babadeda crypto. And we'll do so by showing you our point of view when we investigated something that might have been simple or irrelevant anomaly in one of our customers' logs. And later on, we'll dive into the Crypter's internals and understand how it works and how we use that information in order to uncover a major campaign that targets some NFT communities, including some additional campaigns that targets the Ukrainian entities. But before we start, let me say a couple of words on what the crypter is for those of you who may not familiar with it. Let's do that with an example. Let's say we have a threat actor that wants to use some open source information stealer for some of his criminal activities. If he'll use it as is, theoretically, security solutions would be easily detecting it either by its strings, metadata, or even some of the code blocks. And that's exactly when cryptors comes in handy. They solve this problem by taking this malware or the information stealer as an input and performing some obfuscation, encryption, and code manipulation. And hopefully the output of the crypter is an undetected file. Without further ado, let our journey begin. So, one of our tasks as security researchers is to keep track on current trends and understand the threat landscape and its evolution. And in order to do so, we use classifications to divide the massive amount of data we got from our customers into specific threats or behaviors. And that helps us to cluster the data and follow trends more easily. So one day, while going through one of our customers' logs, we came across an anomaly. Specifically, it was a Crybot, which is an information stealer. And at the time, we had plenty of those infections. But the thing that caught our eye was the fact that the infection chain that led to it was something that we haven't seen before. And the Crybot was being executed from an executable that was being signed by Microsoft, which was legitimate. And at this time, we were taking those first aid ashes, like every person in our field would do, to virus total. Yeah, and we were surprised to see a 0 detection rate, which means that no security solution was able to identify this file as malicious. And we were even more surprised to see that this was the case for multiple scans in a very long period of time. We took an additional hash from one of our prevention logs, and the result was the same. So at this point, we were extremely curious to understand how the crypter works and what keeps that low detection rate. So in order to do so, we need to get our hands dirty and dive into the Crypter's internals. So this is an example of how the infection chain looks. And you can see that it's composed from several components, and we'll explain each and every one of them. Let's start with the installer, first stager. And the installer starts with decompressing its files into a newly allocated folder on the disk. And this is how this folder looks. And you can see that among, it has very files in that folder. And among them, most of them actually, are in fact legitimate. They belong to a legitimate application or some open source application. And the ones that marked in red belongs to the malicious infection chain. Once the installer finishes its execution, it calls the file marked as 1, the executable, And this executable's sole purpose is to invoke the export function of the next stage malicious DLL. And as you can see, it does so with just few lines of code that are placed at the very end of a log function, whereas the rest of the code in that function is actually benign, again, belongs to legitimate application. Once this DLL is being invoked, it starts its execution by calling some additional DLLs, and this part in the crypter is written in a modular way that helps the crypter's users to choose which functionality they want to use. For example, the functionalities that we've seen are, for example, a DLL that performs persistency in some various different ways, and a DLL that can download additional malware, and many more. So once the DLL finish calling those modules, it will load a file from that folder to memory. In this example, it's an XML file, but we've seen many other file formats such as PDF, PNG, and many more. And this file is structured as the follows. In between its legitimate XML strings, we have the first shellcode. Later on, we have a configuration structure. And after that, we have several of encrypted chunks. And once the main DLL reads and loads that file, it will invoke the first shellcode by holding a hard-coded offset to it. This shellcode has several functionalities. One of them is to load the configuration structure that was placed in that XML. And this configuration structure holds the decryption key, and the decryption key for those encrypted chunks, and their offset and size on that file. And those configurations, those encrypted chunks are actually the final payload and the second stage shellcode. And after loading the configuration structure, it will decrypt those chunks and concatenating them to their original form. Then the decryption shellcode will invoke the second stage shellcode, which is the injection shellcode. And this injection shellcode, well, is responsible for injecting the payload to the original process memory. And that's the high-level overview on the infection chain. But for those of you who want in-depth information on that crypter, can check our blog for more information. So why did we name it Babadeda? The following is a code snippet from one of the shellcodes, specifically the second one, the injection shellcode. And if you take a closer look, you will see that there are two D words in there. The one in green, dead beef with a typo, which is known to be used as a magic debug value. And the second one in red, Babadeda, is in Russian stands for grandma, grandpa. So it was an easy choice, as there were no any other indicators to choose from. Moving on to what makes it so evasive. Well, if you remember, we have the code logic that is split to several DLLs, and those DLLs are placed among many other legitimate files. And the code in those DLLs are placed again among many legitimate code. And on top of that, in newer variants, we've seen that the main DLL is being loaded by a newer technique that called the DLL side loading, which helps reducing the amount of malicious files on that folder by one and results in executing the final payload from a legitimate process. As if you remember, we've seen in our prevention log earlier. And in addition, we have the final payload and the second stage shellcode encrypted in some file format, for example, the XML, and they're encrypted, as I said, and splitted. So at this point, we have the couple of logs. From there, we extracted some hashes and understand how the crypter works. And I'll let Hido continue from here.
Thank you, Arnold. So after understanding how the crypter works, we had to figure out what are our next steps. I like to look at analysis and research as two different things. In my point of view, analysis is focused on a specific piece of malware or a specific task, such as incident response. On the other hand, research is a broad field which is redirected as new information revealed. That's actually exactly what happened in our research. We started by looking at the Babadeda crypto itself, and now we are moving on to find its usages in the wild. At this point, we have a pretty good understanding about the inner workings of the crypto. We can use this knowledge to translate it into a Yara rule. For those of you who don't know what a Yara rule is, all you need to know for now is that Yara provides you a convenient and intelligent way to search for byte strings, for bytes and for strings and byte sequences in binaries. So our Yara is composed of three main indicators. The first two are being the Babadeda and dead beef placeholders Arnold just talked about. And the third one are few bytes from the decryption shellcode, which I remind you is not encrypted on disk. Once we have our Yara rule tested and ready, we can use it to hunt for more samples. We hunt in our own data, our own telemetry from our own customers, as well as online malware databases such as VirusTotal and Malware Bazaar. Those databases usually let you use your own Yara rule in order to find for match samples. So after running this sample collection, we had a pretty large database of Babadeda samples that we needed to extract some information from them. So we wrote an automation that extracted some IOCs, which I'll talk more about them in a bit. And then we used open source intelligence to find some references of usage in the wild. So let's go back to the automation and understand what data we need to extract from each sample. To do that, we need to understand what is our goal. And our goal was to find usages in the wild. So we figured out that the sample source, network activity, and the final payload classification will be enough for us. And as you can see, there is an example. This is an example of our automation's output. The left column is the final payload, and the right column is the corresponding network activity, network indicator, which can be your full URL, domain, or IP, or even blank if we haven't succeeded. We used this output to see what malware families made the most use of the Babadeda crypto. So this one was pretty interesting to see. Then after collecting, extracting all of the data, we started open source intelligence. We used online sandboxes, malware databases, social networks, and of course Google and VirusTotal to see any correlation between what we found so far. And that's when we came across the following tweet that matched with one of our samples hashes. The interesting part in this tweet is that it provided us an additional information to work with. As you can see, there is some kind of app called Moonbeam with what's supposed to be its domain, but actually it's slightly different from the original one. And Discord message, sorry, it's small in here, the Discord message that classified as a scam alert. We wanted to see if there are any other services that follow the same pattern. So we took the IP address of the fake domain, and we saw that there are indeed other services listed under it. The most famous one you might be familiar with is a fake domain of Larva Labs. And then we got inside those fake website, looked inside the code, and we were able to find some watermarking that allowed us to write a crawler which will find additional fake websites like those. And after running our automation, we found a bunch of them with one specific common ground, that they are all some kind related to the NFT and crypto communities. The last piece of information we wanted to verify is whether the Discord message is consistent among all of those services. So we entered the Discord server, the official Discord server of each one of them, and we found that indeed they are all having the same Discord scam message. At this point, we understood that there is some kind of an ongoing campaign that targets the NFT and crypto communities, and we decided to dig deeper, and that's what we found. For those of you who don't know, the NFT and crypto communities are highly dependent on Discord as the main communication channel. The attacker knew that fact and used it in order to find new victims. Once he targeted a service, it will add its bots into the Discord server of this service, and those bots will send a direct message to each member of the channel. As you can see, the Discord message has an official looking of username and title. The Discord, the message body calls the victim to download the new desktop app in order to gain access to the latest features. And at the end, it provides a link to the official website, which is different from the official one. For example, in this case, Debunk, the official website is debunk.com, where the provided one is debunk.found. Once the victim falls into the scam message and clicks the link, it will be displayed with a website that looks almost identical, with one main difference, that the login button is now a download button. Yeah. If the victim continues and download this file, it's actually a malware that, upon execution, provides the attacker a full control on the infected system. We decided to publish a second blog post that details about this threat actor, the attack chain, which you can go and read about. Wait. We actually tracked back the activity of this attacker, and we found that it was active since November 2020. And the more interesting part is that since August 2021, its preferred crypter is no other than the Babadeda crypter we just talked about. So that actually explains how we got to this campaign at the first place. We wanted to see some usages in the wild, and we got them. At this point, you may ask yourself, why do we publish our work? Why do security companies and security researchers maintain an active blog? There are actually many answers to this question, but for us is to hopefully make an impact, I think. This figure shows how many new targeted services were each month by this attack chain and threat actor. And as you can see, before releasing our first blog about the Babadeda, there were around 15 new targeted services. And our first blog only briefly discussed about this ongoing campaign. So the impact was, of course, close to none. And then we decided to publish a second blog post focusing on the threat actor, its evolution over time, its infrastructure, and much more. And finally, we got some impact. And as of today, we can say that there are no new targeted services. We can't say for sure we caused it, but for our own motivation, we do like to think so. Okay. Another reason for us to publish our work is to help others with their research. For example, let's take the case of Babadeda against Ukraine. The Ukraine CERT has published that the Ukrainian state organization has been targeted to SaintBot and Outsteal malware attacks. In this blog post, they provided some details, not many, and with some IOCs, but didn't explain so much about the infection chain. Then security company named Telsi took the work and expanded it, and what they found is that Babadeda was used to drop the Outsteal malware. You can go and read more about this. I'm encouraging you. Very good stuff. So let's take a recap of what we talked about today and what are the main key takeaways we want you to take from this talk. We'll begin by understanding the threat landscape you're working with. If you recall, that's how the whole research story began at the first place. We knew how certain malware infection chain would look like, and that helped us to spot the anomaly between the rest of the logs. Look at the bigger picture. Although we started by inspecting the Babadeda crypter and its inner working, we then immediately took a step back to understand what role it plays in a full infection chain in a real life scenario. Use automation to make your analysis easier. When you are dealing with a large amount of data, you must automate as many tasks as possible to make your analysis and research much easier and quicker. For example, in our case, we have automated the sample collection, the IOC extraction, the crawler, and many more components. And finally, share your findings and make use of other findings. This is a great community. Contribute to it. It will help others in their work and hopefully will help you in your future work. Thank you, everybody.
Cool, great guys. Thank you very much for the interesting talk. It was nice to be taken on your journey of discovery, and also, I mean, linking to the keynote from this morning, sharing your findings, sharing what you figured out. It's a really cool thing to help the community. And maybe some of you got interested in also doing similar stuff. So yeah, we have time for some questions. So when you have questions, feel free, come to the microphone.
Between the two blog posts, there seem to be around 4 months, more or less. How much human efforts there is behind this kind of research, and how many people were involved, and was this, let's say, a focused effort on that, or how was this done, let's say?
So, actually, after posting, as I already said, at the first blog post, we briefly discussed about the campaign. So we already knew that there is some kind of an ongoing campaign, but we didn't went in much details and understand it fully. But we keep our eyes on it, and then after a certain period of time, we decided to go back together. We worked together not only because it was is a lot of work to be done, but also because it's fun to work together. And we got back and we decided to investigate more this threat actor. And it was, I think, at the same scale of the first research, but it's different because the first research is more about reverse engineering and malware analysis, where the second is more threat intelligence and those sort of stuff. But yeah.
Thank you.
Thank you.
You had this slide with the bullet points about what made this crypto so evasive. I'm new to malware analysis, but still none of those bullets was really new to me. So is there any really specific thing that made it so evasive, or is it actually not that hard to make crypto with a 0 detection rate? So is it common? Is it a common thing, or is it really that special?
So first of all, it's not that hard to make a crypto so evasive, but the thing that was special here that was the fact that this crypto was evasive for a very long time. That was the what interesting in this part. And it does that by combining all of those bullets, as you said, together. That's how it does that.
Very nice. Then, yeah, thanks again, you guys, for also making the trip from Tel Aviv here to Munich to present. And thanks a lot. Another round of applause.